Hey, thank you everybody for joining today. Today we have Dennis Gallagher, who's going to be talking to us about dust and the study of dust charging at Marshall Space Flight Center. Go ahead and take it away, Dennis.
Okay. The dust work I'm doing with Todd Bradley and Eric Cantrell. It's still I'm doing. I have Marshall in the Dusty Plasma Lab. Last slide is Alex Rodriguez has gotten me wrangled into some things, and we're even started wrangling each other into a project. Dust, you've seen a quote like this before: all the atoms we are made of are forged from hydrogen and stars that died and exploded before our solar system formed. So if you're a romantic, you can say we're literally stardust, which has been said before. Frankly, I like this better. If you are less romantic, you can say we're the nuclear waste from fuel that makes stars shine. I like that a lot better. I wish I could take questions during it as I go, but so be it. So everything came from dust, supernovae. Um, and I don't know if you can see my pointer, but uh, non-volatiles were the first, I suppose, to condense. As they cooled, volatiles began to um, accrete. Ice, various kinds began to accrete on the dust. That material, even though it spins up in the presence of stellar light and charges electrostatically, somehow combine to form larger objects. Um, um, Waves, density waves, shock fronts in space from supernovae, I suppose, collected material together, dust, and when it was sufficiently dense, allowed stars to collapse and other accumulations. Um, as objects were formed, you began to produce more dust. On the moon, for example, solar wind and micrometeorites pummel the top layer of the moon that more and more finely breaks up the material that's there. They call that lunar gardening. Maybe the top few centimeters are that. The image of the moon with the yellow dots, those are where impacts have occurred during a period of time. There's a camera at Marshall and a group that's interested in the space environment of dust and meteorite material, micrometeor material, um, for the purpose of understanding the risks that there are. And all of it, of course, led to leisure time on the moon, I hope, one day. So dust, although it made everything possible, is kind of a problem, an existential problem. Everything in space develops an electrostatic charge, no matter what it is. Ionizing photons, ionizing particles from some micron meters, nanometers, up to very large objects in space without an atmosphere charge. That material gets into everything. You know, our Mars explorers in the Apollo era. I think this is Sherrod, which I probably didn't say right. Were harassed by it considerably. It can get into everything. Seals, gloves, or lungs. It really is a problem that has to be understood. Dust we'll get onto surfaces like solar panels and thermal radiators and cause them not to work as well as they could. They can be levitated into the atmosphere. This is a photo from Apollo era of what amounts to zodiacal light, I suppose, over the lunar surface, presumably due to elevated dust that was levitated off the surface. The trick here is to understand how dust charges, because it charges individually. If the material of a surface is porous, then light, photons, ionizing radiation of various kinds can get through the top layers to the bottom layers. Dust itself charges individually, but because it becomes charged, then the dust behaves collectively in addition to individually. But you have to be able to predict it, and the problem with that is that you can't yet, anyway, theoretically predict very well how dust will behave. Micron-sized dust will behave. The dusty plasma lab, this is one of two chambers, vacuum chambers. And maybe I should say that with a small voice, because this is a vacuum chamber in here, very small. This is about 8-10 inches cube, where the business side of this is. This is one of the versions of the electrostatic trap, electrodynamic trap inside, and fake laser light coming in there. So what can you do with it? You can work at understanding why light from astronomical objects is polarized. It's thought to go through dust. Well, that kind of measurement can be done here. You can look at the photoelectric emission yields from small dust. You can look at the electrostatic or the electron yields. You can look at charging, and it has been done looking at charging in airless bodies. These ones that are arrows that are outlined in red have been published, articles on them. You can look at radiation pressure. There's another chamber in the lab that's being developed to be a cryogenic trap it has a closed loop helium cooler that can go down to at least close to helium temperatures, so that you can study at least into the outer solar system dust in selective gas environments at low temperatures that are characteristic of those regions. A little close up. So small chamber. This is a close-up of the trap that's inside this particular chamber, the church leaf temperature chamber, with a grid on the top, that's hemispherical, and on the bottom, and then a hyperbolic curved center electrode. So these are charged top and bottom, and the center electrode is electrified. This happens to have an ultraviolet monochromator on the side that you can illuminate it with varying wavelengths down to ionizing wavelengths. We've been using it for Lyman alpha from the sun most recently. This is a telescopic microscopic camera. So maybe 5-6 centimeters away from the end of the camera, microscopic grain will be suspended that you can look at if it's illuminated by a laser. You can't see it otherwise. Put a multiplier tube on the far side to look at the flux, monitor the flux from the monochromator. Down below, I'll talk about more later, is a Faraday cup that does the same thing for the ion and electron sources, which are up above. This is a close-up of an injector that we developed that you can put dust on this trough, and a piezo shakes this assembly, and it just trickles off the end into the chamber. And then you can pull it in and out of the way of the ion electron beam source with that. You can't hear it, fortunately, but this thing is oscillating at about 5K to 8K hertz. The grains just kind of trickle off the end here. The trough itself is electrostatically charged or electrically charged to cause a charge, net charge on the grains as they drop through, positive or negative. The grains have to be charged to catch them. This is much like a Millikan oil drop experiment that will suspend grains wherever you want them between two electrodes, two plates. In the lower right is a setup where we can take dust, either lunar simulant or lunar dust. This safe was forced on me because of the archivist at Johnson so that we could have Apollo 16 dust, 1 whole gram of it. You could probably fit, I don't know, 4 of them, 6 of them in the size of the knob on the front of the thing. But we keep other dust in there that's been sieved. This is a siever with a mechanical vibration for the thing and ultrasonic vibration. Different sizes that we can sieve into. Although at the moment we have another way to try to figure out the size. You need to know the size before you can use this. So the production, or so the impact by ionizing sources, photons or ions or electrons, produces secondary electrons. That's a current away. The primary, except for the photons, primary electrons and protons represent the current into a grain. And you determine potential that the grain goes to by the current balance of the size of the grain. And it changes very rapidly as astronauts move across the surface and go from sunlight to darkness. It considerably changes the charge. I've heard of a study where this guy's not doing it, but if you were using a drill to auger into and get a core sample in shadow, say behind the lander or a big rock like this, the drill could charge to 1,000,000 volts electric potential. That would not be a good day. So you really need to understand how things charge. And it affects everything. So you need to understand it. The rate of change of charge is what you need to understand this current equation. That we also need to understand the efficiencies, which are and is in here for the the efficiencies of emitting secondary electrons from ions, from electrons, from photons, and the fluxes of the electrons and ions, and the flux of photons. So these go together to give you the current balance equation from which you should be able to determine charge if you know those fluxes. And so the people at Johnson Array asked us to do this for dust grains, ranging from about 1 micron up to 100 microns, in the presence of the solar wind and solar light, ionizing photons from the sun, so that they could use computer modeling to determine how dust would charge, and they could manage dust better for astronauts on the moon. And well, originally to Gateway, a small space station that was going to be in orbit around the moon until it politically got killed. So that's the going in story, and then vicissitudes occur. This is what it might look like, or what it does look like, where primary electrons or proton or ions eventually be protons. Took me a huge amount of time going through safety, but I don't have now, a bottle of hydrogen gas in the lab that will be used to produce a proton beam. Protons are the primary composition of the solar wind. This is a Faraday cup sketch with an aperture plate that the beams go through, whether it's, well, not photons, but particles, and a collection plate where they simply fall onto the collection plate, causing a current, change of potential, a current through this, and a very low current device, electrometer, to measure the amount of current flow. And that can be used then to derive the flux onto the plate. You needed the flux. Unfortunately, it's not that simple. It'd be nice if it just fell on the plate and it stayed there and it left its charge, whether it's positive or negative. That doesn't happen that way. Some fraction. So when an ionizing flux falls on anything, it produces secondary electrons. And that's the case inside the Faraday cup too, and on the surface of the Faraday cup. Inside, if you have protons or a positive charge landing on the plate, secondaries will come off, for example, and go to the sidewalls. And if that is also part of the collection plate, then no harm, no foul. Negative charge came off, negative charge came back, like here. If it goes to the aperture plate, it's lost. That's a net loss of an electron, and not good if you're trying to measure positive charge or negative charge. It affects the current you measure, and it gives you an error relative to the primary ionizing source. If the beam, the primary beam, is broader than the aperture, then it falls on the aperture plate and it produces secondaries. And depending upon the diameter of the hole and the distance from a collection plate, you'll get a fringe field that's above the Faraday cup and the aperture, and secondary electrons close enough, flying or passing close enough to the aperture plate can be drawn in, and that negative charge deposited, and also change the measured current relative to the primary current that you're really interested in. And all of those things, this is an equation for the current into the Faraday cup and the different sources of current that can affect the measurement of the primary flux, which is really all you're interested in. But you got to get around that somehow. There are two ways. Well, this is a little closer sketch of it. And the diameter of the aperture to the collection plate, if it's greater than 5, equal to or greater than 5, then that cuts down on that on the secondaries off the aperture plate anyway. At the top, you see not a flat aperture plate, but an alternative aperture plate that has a conical middle with a hole of the same diameter as the aperture. And this has a different purpose, and this has a purpose. So it turns out you can take batteries, these are just 9-volt transistor batteries, and you can put them in series with the aperture plate coax, center coax, and charge the aperture plate positively. It does not affect the current measurement through the batteries. You can still make that measurement, but it keeps the collection plate positive, which will draw back secondary electrons to it, so that it might be emitted, but it's collected and no net effect. And then depending upon how many of these three that you put in series with the coax, you'll pick off different portions of the energy spectrum of the secondary electrons that peak in energy around 2 to 3 electron volts, but extend up to much higher energy. As long as the primary beam of particles is significantly higher, then you don't do much with that. So there are two ways now. This is the collection plate that we ended up machining. I made the first injector and the first example of this in my garage, of course. This is machined, it's beautiful. But the idea here is that a primary particle hitting the surface of the cone is going to have a secondary emission pattern that's not entirely known, but you could assume that it might be a sine squared emission pattern with a peak perpendicular to the surface and 0 along the surface. That probably isn't going to make it. So particles coming off of this surface are unlikely to get here. And this is extended significantly further. That's a centimeter high, half centimeter diameter, significantly higher than, longer away from the collection plate than it was with the original manufactured collection plate. Another approach, which is the typical one, the traditional approach, is to use multi-layers with 3, 5 layers, depending upon what you're doing with it. With 3 layers, you can have the first and the second, or first and the third grounded, in the middle charged to negative potential that in and of itself will keep secondaries in, and secondaries from inside that are produced at the collection plate, and secondaries produced at the aperture plate from coming in. The disadvantage of this is that it reduces the flux of the beam coming through. And if you don't want to sacrifice the flux, then you're really just, you have no alternative, and that's why we developed this different kind of plate. So the trap, there are several papers that were published very early on. It's been around for some time. 85 is Davis's paper, where essentially the trap is a top electrode, like I showed you, bottom electrode that are usually charged to the same potential, and a center electrode that's hyperbolic that produces a quadrupole electric field structure. It's electromagnetic because the center electrode is run with a sinusoidal wave from an AC source. There's an aperture, small aperture through the top electrode and bottom, so that you can drop a grain into this. And if you're clever, and there's the art, you can trap it. You can catch it with the vertical electric field. The horizontal AC field is designed to keep the particle toward the center. Of course, the particles are falling in there with some energy, kinetic energy, and so when you stop them, they tend to oscillate around. You're doing it as a vacuum. If you're trying to run an electron or ion gun, or really the UV, you need to be down into the 10 to the minus 5 torr range for that to not burn out your gun filaments, and for the UV to get through it. I may not have to get quite that low for the UV, but it needs to be below 10 to the minus 4, typically. So that's what these things are designed around. This is basic thing. There are some variations that people have used, but that's the basic. If you look at simply in the vicinity of the center, and you want to talk about the dynamics, the orbital dynamics, if you will, of a grain trapped in this electrodynamic field, when you look at the laser and you get an image of it, it looks a lot like a Lissajous pattern on an oscilloscope, where we have two different sources along X and Y axes, that are displayed from two different inputs on the scope. And you can look at the dynamics, and what you find, one parameter beta versus alpha. Alpha is related to the drag parameter, so that depends on how dense the gas is inside the chamber. It's hard to find, but I finally found a paper that demonstrated that when you get into the 2 to 4 torr range, the gas goes from the same drag that you have in the atmosphere at one atmosphere pretty much, to down to from, in other words, thermal to molecular collisions below that range. And so you need to get below that range and in order to only have molecular collisions and drag, and that minimize the influence of the gas, whatever the residual gas is, and backfill it with a noble gas or not. It ends up just from the dynamics having regions of instability and stability in beta and alpha. Beta is relative to the magnetic field strength. The first region of stability from beta 0 up to 0.9 roughly is stable, and then it goes unstable. So, and there are equations that come out of the dynamics based on the frequency of the AC applied to the center electrode, the separation between the top and bottom electrodes at the center of the trap, the vertical electric field, the horizontal AC electric field, gravity, gravitational constant, and chamber constant. It seems like wherever you go, whatever you do, there's always a fudge factor that relates to, in some way, the mechanical characteristics of the system you're looking at that remain constant for that particular system. And in our chamber, we determined that to be 0.47. You do that by having a particle trapped as stable as you can get it, not bouncing around too much, and, and changing the parameters, lowering VDC, raising VAC, raising the frequency, oscillating frequency until beta comes up high enough that the particle goes unstable and you lost it. At that point, because you were in this first region of stability, you know that beta is equal to 0.9 roughly. And that with that, you can calculate the trap coefficient. The thing we're exploring right now, which ought to work, is to be able to measure the grain radius, the mass and the radius, by knowing the charge of the grain, this is the voltage on a grain that's dropped into the system, based on the trough potential and the mass density of the material that you're working with. There's another way you do it. It's called a spring point test. That's been used historically, and that's where you also vary the conditions at vacuum and or around. I get not vacuum. I mean, it's at vacuum, but it's above 3 torr, 3 to 5 torr. And you have atmospheric drag in that case. And again, you vary the trapping conditions until the particle just begins to go unstable. And you can use that to measure get to the mass of the particle. The unfortunate part of that is that you can also lose the particle. So if you're using Apollo grains of dust, you don't really want to do the spring point test to find out the size of that grain that you then can't do a charging test on because you lost it. And so you got to find another way, and this is a way that we're looking to make sure that that works. You can determine the charge for mass, and you can get the mass out of it. You can do the charge, and then you can get the mass out of it. So this is the process that we're doing, where for determining efficiency or yield, we're not going to yield, and I can explain that too, but is to look at the change of charge, number of electrons per time, to get the flux of secondary electrons off the grain. And what happens is, as the grain potential, let's say it's a negatively charged particle, that's positive in the top electrode or negative on the bottom. As the grain gains positive charge, then it'll be pushed down. And you change, if you keep it in the middle by changing the potential, the voltage across the top and bottom electrons, then you can trap the potential of the grain and use that to determine the change per unit time of the charge on the grain. You do the same sort of thing with a photoelectron efficiency. You have to divide by the flux of the beam in either case. And so that works out pretty good. We do this again below 10 to the minus 4. But you got to be really super careful. It takes nothing to knock the grain out of there, which is another reason not to do the spring point test, because you have to operate in the 10 to the minus 5 range to use the particle beams, particle guns. But you got to get there from where you do the spring point test if you use that method. And there's quite a hurricane in there as you're pumping down, even from 10 to the minus, or 10, even from 10 torr, 2 torr, down to below 10 to the minus 4. And it's hard to keep it in there. You walk across the room and it vibrates. But that's not enough. There's even more trouble. But I'll get to that. So what you want is, well, this is it, is that you want, and we were asked to provide secondary electron efficiencies as a function of grain charge, type of grain, and we've been using JSC1A, which is a surrogate that's produced on Earth. It's supposed to have the same content as, or similar content as that we got from the moon. with the Apollo missions, made from volcanic material primarily. Or we use Apollo material when we can get it. And trust me, you got to bleed for that. It took me 2 years to get 1 ounce. But you want to know the efficiency of charging, and it changes with these different, the size and the potential of the material, and that's what we're doing the test for. But what happens is that the charge is not uninhibited as it charges, it saturates. And so, and it gets there within a matter of minutes or seconds, depending upon the connectivity of the grain. And so, while there's a period when there is a linear slope in the charge on the grain versus time, and you can measure a single dq/dt, you get a single efficiency for the emission. That doesn't last. It saturates, and it's just as important to know the saturation potential. If things are stable in the environment, the ionizing flux to a grain, then it's going to get to saturation, whether it's going negative or it's going positive. But there's more, and this is above and beyond the fact that the first time we used the electron gun and ion guns that we had in the chamber, had in the lab, they both broke. And they were, the ion gun was so old, it cannot be repaired. The electron gun, when it broke, we found that it was just old, just young enough that it was going to be the last of its breed to be repaired. There are no more spare parts for that electron gun. We have new ones now, and so life is back to normal, more or less, but that's such a problem. Don't go into the air in an aircraft that hasn't been maintained. But there's more. The beam itself, in this case, it's the UV beam, was once measured to be about 175 to 140 microns. The particles will oscillate around around the sweet spot, the equilibrium spot in the trap, and go in and out of the beam. And so it does you no good to include the time that the particle is out of the beam in a calculation of the Q/d, because it's not changing. The Q is not changing when it's out of the beam, but time goes on. These are measurements that we made with the collection, the photomultiplier tube, to get the size of the beam, both in pixels, 40 by 18, and previously it was measured in microns as well. And so what happens is these are measurements of the Y position and the X position. So we use a computer in LabVIEW and a camera to watch the particle and automate it, keeping the particle in the middle and recording in a regular time interval the voltage required to keep it in the middle, as well as the current if you received the photomultiplier tube or through the Faraday cup for particles. Based on the motion, we need to try to understand when it's in the beam and when it's not, whatever the beam is. And this is a case of the ultraviolet source, limiting this to this, and then knowing what periods of time you can use to calculate the flux. It makes a noticeable change in the behavior of the voltage required to keep it in the trap. And so it would make a noticeable change, measurable change in the efficiency. And since that's the objective, then you have to take it all into account. When I've been doing this all through graduate school, I've seen quadrupole fields before, but I've never, mathematically. And you look at math and it gives you an impression that you build an image in your head. One time we ended up catching hundreds of particles, a lot of particles in the trap. And this is maybe 100 microns from top to bottom. and you could see the quadrupole, which I thought was super cool. And um, so I couldn't help but show that. Last is maybe most of you know Alexis. Um, he's a walking fountain, cornucopia of ideas. You can't get close to him and try to talk to him about his stuff and give offers of suggestion before you're suddenly a co-author and you're doing work. Dangerous person to be around. Wonderful person to be around. And we've given each other ideas at this point. This one is focused on the fixation of nitrogen in basaltic surfaces, surfaces. I am not a geologist. Give me space flight for physics any day. Or in this case, charging. The idea here is that it used to be wet and warm on Mars, not super wet, but wet enough and warm enough that it rained. And if you have the proper surface and you have a droplet, a large droplet, the gravity on Mars is less, so you're going to get bigger droplets. And when that hits, it's going to splash. It's going to produce a conical splash of material. And another way to charge is called, well, I put it up here. Anyway, you can charge by friction. Same thing that happens when you slide your feet across the floor carpet in the winter in northern latitudes, and maybe anytime in Tucson. I'm not sure. I haven't tested that. Triboelectric charging, any kind of friction, and you're going to get friction, and you're going to get the material that's in the splash to break up into small droplets, mini droplets, micro droplets that could be charged. And there's a way to go around determining the charge. And the electrostatic Paschen breakdown is that voltage for a given atmosphere and composition, where a potential of a difference over a particular distance, if higher than the Paschen breakdown will discharge. Lightning occurs because of that. I've got a graduate student I'm working with who's studying lightning on Mars, or mini lightning, micro lightning on Mars, near the surface. And that can produce a discharge. It's a source of energy and a mechanism for Fenton process that can fix nitrogen in the soil. And apparently there are regions, I'm a geologist, where this is a deal. You want to know how that came from? This is prebiotic, I guess. I don't know. There's something going on there. And they're among those that are working with Alexis are those that know about the chemistry and about all the different aspects that go into this, the geology, whatever. Mario is developing, this is a paper, sort of the last sort of figure, I think, in the paper that gives a cartoon of the process, and he's working on that. This is a draft. We're also, Alexis has got me involved in fault scarps on Mercury. How do you have a cold sun and a warm earth? And I've gotten him, and the two of us have gotten each other in trouble here. How do you form the smallest rocks, essentially, pebbles, out of multiple grains if the grains are spinning? And they can spin up to 10,000 hertz, RPM, revolutions per minute or per second. And if they're doing that, they're going to be thrown apart. They're going to be drawn and quartered. And how do you keep them together in that environment with suns shining, stars shining, and keep them together? That's pretty cool. I gave a talk at Johnson of some experts in this kind of field. We got terrifically excited that we could do some of this in the dusty plasma lab, the cryo chamber. Accrete ice of various kinds and spin it up and possibly watch that process occur. Try to figure out how it can occur. But that's all I've got. If there are any questions, I hope you'll ask.
I have
If I was going
uh,
to say, if I put you all to sleep, I'll make a loud noise. Go ahead.
a couple of questions actually. If you take two dust grains, say one has a surface area 100 times the other, um, do you get a charge which is 100 times? So that
It
is one
changes,
question.
yeah, it
Uh,
changes the capacitance. The grains are, except for the iron-rich grains, they're dielectric. And their capacity, their capacitance, will determine the potential for a given amount of charge, net charge within the grain. And so if you had the same charge amount of, excess electrons or deficit of electrons in two grains of that kind of differing size,
mhm.
a planet and a moon, then you'll have a lower potential on the outside of the larger grain than you would on the other. But they will also induce a dielectric charge on each other as approach, a mirror charge, if you will, on each other as they approach. So yes, they'll both have potentials. They'll behave a little bit differently, larger mass, lower voltage for the big one. And so their dynamics will be, influenced. But yeah, they'll charge just fine, just like you do when you walk across the carpet and you annoy your pet by sparking on its nose.
Uh, the other question is uh, when you look at icy dust particles, uh, what is the effect of having ice on that dust particle?
Um, well, ice itself is not a very good conductor.
Hmm.
How it changes its efficiency for charging is a great question, and the reason why we're building a cryogenic chamber so that we can make a measurement. Or, as a function of grain size and material and temperature, because different volatiles can accrete onto grains and have different behavior. Um, there's just all sorts of interesting things you can do. You can go to temperatures that are more characteristic of the outer planetary and space environments and interstellar space. We can't go to those temperatures with a helium cooler, but we can certainly get there. The real challenge, and I'm sorry, but this is just cool. The real challenge with the building a cryo chamber is that two things. You have to cool the whole trap. And we have to have insulators between top and bottom and center electrodes. And we have been using a material that's a great electrical insulator and unfortunately a really good thermal insulator. And we can only cool one end, the bottom electrode. Replace that with another material. Found it, had to work with material people at Marshall to find a material. They were going to make it for us, a custom material. And they were all set, had a material ready to go, and COVID shut us down. By the time we opened back up again, their material was gone. I don't know why. But they found us a company that could take the part of the material is most like diamond, and diamond would be the perfect material. Low electrical conductivity, high thermal conductivity, but the next thing down it, I can't think of the name of it at the moment. And they could sinter it into a solid piece and use diamond cutting to shape the pieces we wanted. Got that solved. Okay, the next is that you need to know the temperature of the grain. It's in a vacuum. You can't touch it with anything. You can't use the infrared sensor that you want to use that is in use to measure your temperature because the wavelength is too long. How do you do it? Well, what we're testing right now is to use quantum dots, which I knew zero about. But a materials guy said, why don't you check it out? I think quantum dot temperature, so quantum dots scintillate when exposed to ultraviolet light, a narrow wavelength range. It scintillates in visible spectrum, and at least for material that we can't touch because it's too toxic, the emission spectrum in visible wavelength shifts with the temperature all the way down to liquid helium. From shirt sleeve down to liquid helium, the spectrum shifts. And if you know the spectrum, the emission spectrum, and you've calibrated everything, you can know the temperature of the grain. So you take a grain and somehow you get sprinkles of quantum dots on it, and you expose it to ultraviolet light, measure the spectrum, and you know the grain temperature. And there's more to it than that, but that's something we're doing right now.
Okay, thank you.
Any other takers?
All right. Well, if there's no other questions, thank you so much, Dennis, for this
Sure.
presentation. It was very, very interesting. We'll go ahead and stop the recording now, and we'll be in touch.
Great. Thank you.
Yep, thanks.
Bye-bye.